While we wait for the official start time, any questions in the room or online?
So, you said you will have to go to Brazil like in February?
Oh, so I uploaded to the Dropbox a revised syllabus, and I'll lecture today and tomorrow, and then next week Ann will lecture, and then I'll be back. So tomorrow we'll hopefully finish talking about 2D NMR today. Tomorrow will be the first lecture on relaxation, and then Ann will lecture next week on tensors and MAS and in the solid state NMR. And then once she introduces tensors, we can go back to relaxation theory and do it in the general sense, the block or the BWR theory. So if you take a look in the Dropbox site, you'll see both the new syllabus, problem set 3, answer key for problem set 2. I'm sure there'll be at least one more revision of the syllabus. I don't think we can get through a whole semester with only one revision.
Do we have midterm exam?
Yes, and I'm trying to work out with Ann whether that will be a midterm we give you over Columbia spring break or after Columbia spring break. But I should know that by tomorrow.
Mhm.
So for the people online, we'll start at 1:10 to give Columbia people a chance to get here. If we do finish talking about 2D NMR, tomorrow's lecture is my favorite lecture of the course. If you look in the Dropbox folder, it's called something like NMR Relaxation 1 Brazil 2024, because it'll be the start of what I teach next week. And the PDF file should have some movies embedded in it. And depending on how your PDF reader is set up, for reasons I don't understand, the movies may pop up in another window. You may have to give some permission for that to happen, or they may pop up in the PDB itself. or PDF itself. But,
I have to say that would be unique.
but I don't know enough about movies embedded in PDF files to guarantee the behavior. So I've tried it on 2 different computers and they behave differently on the 2. So no guarantees. But I think the movies will run eventually. Anyhow, right at the end, last time, we looked at the HSQC sequence, and I pointed out that we could break it into 4 pieces: an initial inept period, the frequency labeling period, and then a reverse inept, and then acquisition, which of course we don't need to actually do any calculations from. And then we worked out for each piece the evolution starting with proton magnetization. So here is this initial inept sequence. And we see that it generates longitudinal 2-spin order. So for the rest of time, if we recognize this inept block, we don't have to do detailed calculations. We know we're going to end up with longitudinal 2-spin order after this final Y pulse. And then in this section, the frequency labeling, we have chemical shift evolution of the S spin. Actually, do I have an error? So the first pulse created transverse nitrogen magnetization, and then we had chemical shift evolution, and the last pulse puts one component of that evolved magnetization back up onto the z-axis into the symmetric state, and there's a component that stays in the transverse plane of the S spin. We then have the reverse inept sequence that takes the symmetric state back to IX magnetization, which we then detect. And then this antiphase term gets turned into a multiple quantum operator, or a superposition of single and double quantum coherence, and we don't detect it. So we end up with a signal that's cosine modulated during T1, and then eventually to get a 2D spectrum, we have to get the sine modulated component. And we'll do that by taking a second experiment in which phi 1 is shifted by 90 degrees, and that'll shift the signal to be the sine modulated component that we detect. And we'll come back to this. The main point is just review that we want to recognize blocks. Yep.
If during the net blocks, either I or S is coupled to a third spin, will that get refocused?
Right. So, for example, if this is the amide hydrogen and the protein is protonated, there's going to be evolution of the scalar coupling to the alpha. So if one does, so of course, then what should we do about that? And of course, the coupling constant here for the nitrogen is about 93 hertz. And the coupling constant from the amide hydrogen to the alpha hydrogen is at most about 12 hertz. So not so much of the 3-spin operator builds up, but of course, if that 3-spin operator turns into some detectable magnetization at the end, there's going to be some unexpected small peaks in the spectrum. And most of the time in this sequence, they're not so important. I think in a minute when we look at the HMQC, you see those peaks arising as artifacts that kind of drill a hole in the two-dimensional peak you're looking for, and then you can try to purge them, say by applying a pulse that converts them into multiple quantum or transfers them to coherence on the alpha hydrogen, in which case they're in a different part of the spectrum.
Can I ask a follow-up?
Mm-hmm.
My protein is 15 and 13 syllable. Then, for example, during the nitrogen evolution or for nitrogen,
Right.
do I have to place pulses on the
Right. So now, if this was carbon-13 labeled, during this period, you're going to have, well, again, during this period, there'll be evolution of the I spin coupled to the carbon-13. But those are pretty small couplings. And anyhow, this pulse in the middle will refocus those couplings. In here, you're going to have couplings between the nitrogen and say the carbonyl and the C alpha. And if we want to get rid of those, we have to apply 180-degree pulse on the carbon channel. And usually we can't do it in one pulse on both carbonyl and C alpha. So then you'll have, potentially two back-to-back pulses, or you might just wondering if I have a marker. So right now that evolution, no one online can see. So right now we just have this pulse in the middle decouples the proton scalar coupling to the I spin. And if you decided you just needed to decouple the C alphas, you could then put a 180 on the C alphas, also right in the middle. And now if you wanted to do the carbonyls at the same time, there would be kind of two choices that people use. One would be to say, well, the coupling constants aren't that large. So if the pulses aren't exactly in the middle, there's going to be a small amount of evolution, but it's going to be small. So you could do for example, just do the C13 pulse there and the carbonyl pulse, shift the frequency and do the carbonyl pulse right next to it. And no one can really see that. This sort of trick is okay as long as all we need to do is invert a Z operator if we had transverse C alpha, say, and we wanted to put, needed to put a pulse in the middle, the pulse actually has to really be in the middle. Otherwise, the chemical shift evolution doesn't get refocused. So sometimes you have to decide which pulse has to go exactly in the middle of some period and which ones can be offset a little bit. And as long as you're just inverting Z magnetization, the coupling constants aren't that big, being offset a little bit isn't a problem. The other thing that you'll see happen, though, is now do this, T1/4, and now one of the 180s, T1/4, 180 on the hydrogens, T1/4, 180, T1/4, 180 in the middle. And then we decide which one of these channels do we want to be carbon alphas and which one carbonyls. So at the cost of 2 pulses, this refocuses this period, this refocuses that period. So everything is refocused. This one refocuses. So if this was, for example, the C alphas and this the carbonyls, that will do the trick. And doing that in, as we may or may eventually get to about various experimental details when one is applying adiabatic pulses or shape pulses to do this over a wide frequency range, or tuning the pulse amplitude to where you get a null out of the carbonyls or the C alphas, where you might have to worry about phase shifts. Sometimes having 2 pulses lets you compensate the phase shifts. So rather than being a detriment to have 2 pulses, it in fact helps you with phase artifacts. So depending on the experiment, the short answer is depending on the experiment, you'll see this sort of thing done in multiple different ways. Since most of this is now all coded up inside of the pulse sequences, unless you have some reason for not liking the choice, for example, that Brooker made in their library, you pretty much go with how the program or the pulse sequence is coded up, either in the library from Brooker, or a sequence you got from another lab. So it's a little hard to remember how much time was spent worrying about these little things when the sequences were developed. Just as one oddity to drive that home, you might notice that there is a little asymmetry here. Lots of times in pulse sequences, we like symmetry on the theory that symmetry usually helps with artifacts somehow. But you can see there's some asymmetry because there's a Y pulse here and an X pulse here. And it turns out having them be 90 degrees out of phase reduces some artifacts. And I forget who, maybe Ad at one point wrote a paper basically about why that should be, these 2 pulses should be 90 degrees apart from each other. And of course, today you couldn't possibly write a paper about 1 pulse phase. But at one time, these were important because there were artifacts, and now it's all just coded up for you. Now, the other something on my screen that I don't want there. It's better. The other way of doing this transfer is called the HMQC experiment. And HSQC stands for heteronuclear single quantum coherence, because that's the operator present during the T1 period. And HMQC stands for heteronuclear multiple quantum coherence, because during the T1 period, we have multiple quantum, but the 180-degree pulse refocuses the chemical shift of the hydrogen spin. So we just get the frequency labeling of the S spin, the carbon or the nitrogen. But you can see potentially there's fewer 180-degree pulses. So initially, when spectrometers didn't work so well, and 180-degree pulses were even worse than they are now, this was a considerable advantage, having fewer 180-degree pulses. But we can work out, the operator is exactly the same. We know right from the start that this will be a spin echo on the I spin, so there's no chemical shift. The scalar coupling evolves during this first period 2 tau, but then this 180-degree pulse is going to change whatever operator we had into some new operator. And then here we'll have scalar coupling and chemical shift evolution of the S spin, and then we have J coupling coming back. It turns out that the J coupling between the I and the S spin isn't active during this period anyhow, because it's multiple quantum, and I'll review that in a second. And then here's an example where I recognize that this multiple quantum term is never going to become observable. So I just dropped it at this point, rather than calculating what happens to it during this 2 tau period, which just generates a lot more work without contributing to the signal. And again, we get something that's cosine modulated. Now here, of course, because during the T1 period, we have the transverse proton operator, the proton couplings all will evolve. In the HSQC case, the proton was a Z operator, so the couplings to other protons didn't evolve during T1. Now they will evolve during T1, and that actually has an effect on the spectrum. You can see the distortions in the line shape caused by those couplings evolving. But I haven't done it here. I haven't worked that out. We've done this before, that the 2 transverse operators are a mixture then of double quantum and 0 quantum coherences. If we write each Cartesian operator in terms of raising and lowering operators and then multiply them all out, we have double quantum plus 2, double quantum minus 2, and then 2 0 quantum terms. And as we said at one point already, if we look at the energy level diagrams, we can see that the double quantum coherence is not affected by the J coupling, because both levels move up together, and the 0 quantum are not affected by the J coupling because both levels go down together. So here's an example that if we have a third proton spin called K, the coupling evolves during T1. So we have a cosine modulation with the coupling, and we have a sine modulation with respect to the coupling. So we end up with 2 terms. One is this antiphase term that is cosine modulated during T1. So that's an absorptive doublet. And then we have this second term that shouldn't be there. It's sign modulated with omega s, and it is 90 degrees out of phase relative to the signal we want during acquisition. Because here we have a Y operator during acquisition, here we have an X operator. So these are to give dispersive signals relative to our desired signal, and we have a multiplet component. So I don't have an example, but if we took a spectrum to a large value of T1, we took a very, very high resolution in the indirect dimension, you can see holes drilled down in the middle of the peak because the dispersive line shape is 0 in the center. So you end up losing signal in the center from these positive and negative lobes.
I have one question.
Hmm?
I think just on the previous slide or before that, you had shown that one of the terms is dropped.
Mm-hmm.
The IXSX term is dropped. Does that mean that this experiment is less sensitive than the HS?
Well, that half here that I got rid of, that's equivalent to this half in the HSQC. So in both of them, I lose half the signal because the magnetization rotates down into the transverse plane. It rotates, so there's an X and a Y component, but the 90-degree pulse after the T1 period can only flip one of those back to the Z axis to generate the symmetric state that leads back to the hydrogen. So in both cases, we lose half the signal. And then we have to acquire a second experiment in order to get the sign modulated component in order to do the Fourier transform.
Has anybody built pulse sequences where both components can be read out in the same scale?
So there's basically two experiments where that can be done, or two types of experiments. And in each case, you have to generate a Hamiltonian that can transfer two orthogonal signals at the same time back to detectable signal. And that's possible in a Toxie sequence because a Toxie sequence, which we haven't really talked about, and it'll come up when we talk eventually about average Hamiltonian theory, a Toxie sequence is designed to produce an isotropic scalar coupling Hamiltonian. So then you can transfer IX and IY on one spin to IX or to SX, SY on the other spin. And that way you can take the orthogonal operators and transfer them. And the person who realized you could do that in a Toxie experiment and keep both components, and therefore you would gain √2 worth of signal. You don't gain 2 because the noise is in both, but the noise is uncorrelated. So Mark Rance figured that out in 1989, 1990. And then in the HSQC experiment, you can do it because, again, this operator here, because it's two transverse operators, the scalar coupling doesn't evolve. So at the end of this period, right at acquisition, when you have these two operators, it's possible, rather than turning on the receiver, to store this back on Z, put in a proton pulse. And if it's a proton Y pulse, you put this back up on Z, where it'll just relax slowly by its T1. This stays Y. And then if you put a Y pulse on the S spin, This flips up to the Z-axis. You now have anaphase coherence. You can have another inept period, refocus that back into in-phase proton, and then apply a pulse to rotate the other one down. At that point, you have an admixture of sine and cosine, which is called phase modulated. You can't directly transform that to get a good looking spectrum. But when this refocuses, you're going to have IX magnetization. So you apply an X pulse and bring the other component to Y, and then you do another experiment and bring the other component to minus Y. And then you can add and subtract those two data sets and have cosine modulation, sine modulation. And again, you gain a factor of √2 minus some relaxation loss here. There's a little bit of trickiness because during this period, or the next one, the double inept, these operators relax at slightly different rates. So you have to worry about that a little bit. It turns out that, anyhow, I thought this up. So that's probably my most cited paper in NMR. After I heard Mark talk about doing it with the Toxie, I worked out how to do it with the HSQC. And then you don't get quite √2 because the sequence is longer. There is this headache of balancing the relaxation pathways. And then Lewis K showed that you could do this, you could add gradients in, and that would get rid of these unbalanced pathways. So mostly now we do this with gradients, but the sequence is still longer. But you'll see that when we get to the triple resonance experiments, they almost always incorporate either this sequence, this extended sequence, or the Trozy sequence. It might be my most cited NMR paper, and it's my first one. It's just a little weird. Now, I'm just going to talk a little bit about sampling. And if we're going to do a Fourier transform, then we have to sample the signal at evenly spaced time points. And the spacing, then, or sampling interval, I'll call delta t. So our signal is sampled at some multiple of delta t. And it turns out there's something called the Nyquist frequency that defines, depending on the sampling time, what frequencies are going to be represented in the Fourier transform space. And there's a sampling theorem that says that if we have a signal that's bandwidth limited, the frequencies are within a certain range. If we sample such that our Nyquist frequency is larger than that bandwidth, we will represent all the signals properly. And if that's not the case, of course, other things will happen. So that means then for us that the frequencies in the NMR spectrum will go from minus the Nyquist frequency to plus the Nyquist frequency, or the spectral width will be twice the Nyquist frequency or 1 over the sampling time. So if you have to cover, if your signals are spread out over a large bandwidth, you need a small delta t. And if your signals are in a narrow bandwidth, you can use a large delta t. This isn't so important in acquisition because you have to wait for magnetization to recover the Boltzmann equilibrium or something approaching Boltzmann equilibrium before you can start the next scan. So there's plenty of time usually to record all the data you want, covering whatever bandwidth you want. At least for, you know, proteins and nucleic acids without weird metals that might have some enormous chemical shift range. But if that's not the case, if we have signals with frequencies outside of the range defined by the sampling, then peaks will appear at artifactual positions. And this is called folding or aliasing. And sometimes this is to our advantage. So here's why the Nyquist frequency comes up. It just turns out that to accurately sample a sinusoid, you have to sample twice per period. And if you have higher frequencies, you can see I can create a higher frequency, the dotted line, that goes exactly through the points I've sampled for the solid line. So when I do the Fourier transform of the sample data, the dashed line will appear right on top of the peak for the solid line, because the points I've sampled, they're identical. And if I want to sample the dashed line more accurately or faithfully, I have to sample much faster so that I get 2 points per cycle. Now, where the peaks turn up in the NMR spectrum depend on how we collect the data. And there's basically 2 ways. In one way, the edges of the spectra, so let's think about T2, because this really isn't much of a problem during T1. Let's think of, because we're in T2 in acquisition, as I said, we can sample usually the bandwidth. But in T1, so here in A is the real spectrum, but I've had to use a small value of delta T to get a large spectral width. And now I'm going to make delta T too small so that these 2 peaks, the square peak and the triangle peak, are no longer inside the Nyquist frequency range. And I want to know where they end up in the spectrum. And depending on how the experiment is done, there'll be 2 ways that they get artifactually placed. In one, the edges of the spectrum look like mirrors, so that the peak that should be down here looks reflected along the edge of the spectrum, and the peak that looks up here looks reflected over the edge of the spectrum. And this happens if we collect the data, because remember, we have to collect the sine and cosine terms separately in T1. This happens if they're collected with something called TPPI, which stands for time proportional phase incrementation. But these days, most of the experiments use what's called states, frequency discrimination after David States, who was author on the first paper that did this. And in this case, the edges of the spectrum look like they're connected in a circle, so that you have a barrel, and peaks that rotate off the top just appear on the bottom. So the spectrum looks like it's continuous, but it's just a circle. And the signals just wrap around the circle until they end up in the spectral, in the Nyquist range. This turns out to be convenient way of acquiring the data, particularly for carbon spectra, because the carbon-13 proton spectrum is roughly diagonal. And if you reflect, everybody piles on top of each other. But if you rotate so that the top ends up at the bottom, the peaks tend to fall into empty space, so that we can make delta T larger than we normally would without confusing ourselves. So if we look back here at this spectrum,
Red.
here, these peaks, our spectral range here runs from something like 135 to 100 parts per million. These peaks in red are really up at about 85 parts per million. But because this edge acts like it's connected to this edge, these red peaks just wrapped around and they're in here. So if this upper edge is 100 and these are at 85, they will appear 15 parts per million in from the lower edge. They're 15 parts per million of the upper edge, and they'll wrap around to look like they're 15 parts per million in from the lower edge. So they look like they're about, let's say, 125 minus or plus 15 would be 140, and something like that. When we do this, when we set this experiment up, actually, you can see we don't want these peaks to land on top of the backbone amide peaks. So, initially one fiddles around a little bit with how big delta T is to make sure that the peaks that you're folding don't end up obscuring peaks you really care about. And probably, I think these are probably either some backbone arginine ADA signals or some lysine signals. And actually, we probably want to put them there. So this probably wasn't the best choice. Probably should have adjusted the spectral width a little bit. If I made the spectral width a little larger, then these signals would end up here somewhere, in which case they'd be out of the way. So in the beginning, with the protein, usually you fiddle around with this a little bit so you know that you have the folded signals in a region where they don't obscure the other signals. Now, you can see these have opposite phase. And again, this depends on the details of how the experiment is set up. We could have those signals have the same phase as the unwrapped signals, or we can have them have opposite phase for an odd number of wrappings. And it's really just up to how you set the experiment up. Sometimes it's convenient to have them upside down because then you can see them. Other times we have experiments where the signals could be upside down or right side up for the normal signals, in which case it's not really helpful to have the folded peaks in and out of phase. So it depends on the experiment. Of course, we won't really talk about it very much, but the fact that to do a Fourier transform requires that we sample every delta T is inconvenient if we're doing a 3 or 4D experiment, because you spend a lot of time sampling, far in excess of how much sampling you need for signal to noise. And nowadays, there are experiments called NUS for non-uniform sampling, where you only sample some of the points. In a 4D experiment, you might be sampling only a couple % of the full cube of points. And then there are numerical algorithms that can reconstruct the spectrum. We can't just do a Fourier transform because there will be artifact peaks from the sampling schedule in the spectrum, but one can reconstruct. So certainly these days, a 3 or 4D experiment might very commonly be done with non-uniform sampling and then reconstructed. 2Ds still are primarily fully sampled, I would say. So let me think where we are. Oh, good, we're almost done. the math that I've shown so far has always been written as a continuous Fourier transform, an integral. But our signals are sampled discretely on the machine, either because in T1, we increment a delay ourselves, but in the acquisition, the continuous signal is digitized by an analog to digital converter and stored as discretely sampled data. So here is the continuous signal. We have some intensity, we have a frequency. Lambda here is the relaxation constant. We have our time. We may or may not be able to start acquisition at time 0. Ooh, this thing is not charging. Why is that? Wait, that means it's charging. We might not be able to start sampling exactly at time 0. In T1, we have two 90-degree pulses usually flanking the T1 period. And you know, since those pulses aren't infinitely strong, there's some phase evolution that happens during the pulses. Plus, we can't put them directly together. There's usually some short delay, at least to allow phase switching. And then there may be some phase offset because of the phase of the pulses, evolution during the pulses, et cetera. So in the ideal case, T0 might be 0 and phi 0 might be 0, but in realistic cases, that's not always going to be true. And then, of course, we can do the Fourier transform. Some of the terms here are constants and can come out from the integral. And then, at least in the continuous case, we do the integral and we have, again, our real and absorptive signals. But now, in the discrete case, right, the signal is digitized, so the integral is replaced by a sum. I have all the same factors, but now I have a sum rather than an integral. And it turns out that I can analytically do that sum, or at least Mathematica can do the sum. And this does not look exactly like this result. This is the result for the continuous Fourier transform, and this is the result for the discrete Fourier transform. And the question is, when are they different? So they're identical in a number of cases, but the two that are most interesting for us is first, if tau 0 is equal to 0, and we multiply the first point of the free induction decay by a half. And if you use most processing packages, you'll notice that there's an option to multiply the first point by some number, and it's almost always 1 or a half. And the half is because of this effect. And the other useful option is to set tau 0 to be half of the sampling time. In that case, there's some evolution. Your first data point already has some evolution. But then that can be corrected with a first order phase correction. And then the first point doesn't need to be multiplied by a half. And it's quite easy to get this wrong, but one of the things you'll see if you handle the first point wrong, and then lower the base plane, so you can see the base plane, you'll see big streaks of what looks like T1 noise. If the first point isn't handled right, and then when you handle the first point correctly, those streaks should go away. This delta T over 2 is convenient because, again, if over here, back to the board. I don't know who really first realized this about the Fourier transform, the discrete Fourier transform. Certainly, I think of the person. I think I did something wrong. Oh no, we have the board. The person I think of at least introducing it to NMR was Dennis Torshoff at the NIH, who thought up a lot of clever things over his career. It's also related to something called the Kramer's-Koenig theorem, and I uploaded a paper. It turned out that the real and imaginary parts of the signal aren't independent of each other. And that paper has a nice explanation of what the consequences are. In any event, if we came back here, what is the smallest value we could possibly have of T1? And so we know, because the pulses, the 90-degree pulses, are infinitely short, we know there's going to be some phase evolution. And that phase evolution we worked out looks like a little delay equals 2 times the length of the 90 over pi. And over here, we'll have the same little delay. And then we have the length of this pulse. On the I spin, and then maybe a couple of microseconds to allow phase switching, etc. So our initial value of T1, even if we in the program set this delay to 0, we're not going to have really 0 phase evolution because we'll have phase evolution during all of these. But I could then say, I'll set the initial value of T1 in such a way that this whole sum is delta T over 2. And if I do that, I will have phase evolution to match my second criteria. My first point effectively looks like evolution by delta T over 2. So then when I Fourier transform the spectrum, I'll apply a 180-degree phase shift, and the spectrum should then look perfectly phased. If for some reason I really wanted there to be a 0 first point, and effectively 0 first point, then I'd have to fool around and put in a little spin echo and a delay over here. And here's the other 90. And now I figure out what the smallest value I can set T1 to in my pulse sequence, say 3 microseconds. So here's 6 microseconds plus the length of this pulse. And I set delta equal to that at the start of the experiment so that I get a spin echo that refocuses all of the evolution for the first point. And then I increment T1, but I leave that alone. I don't increment that. And then I'll multiply the first point by a half, Fourier transform, and I won't need any phase correction. Doing this doesn't require adding in an extra pulse usually. So this is quite common to try to adjust the initial delays to delta T/2. On the other hand, you can see depending on the length of this pulse, that might not be possible. Because if this pulse is longer than delta T/2, my calculation is never going to work. And in that case, it becomes more common to put this delay in and use the spin echo trick. Or it could be there's already, for other reasons than the pulse sequence, there already is a 180 somewhere that you can use for this trick. The reason for doing this is that a first order phase of 0 or a first order phase of 180 degrees generates an undistorted base plane. Other combinations, if we didn't do any of this and just had some arbitrary phase evolution in the first increment, we'll be able to get rid of it with a first order phase correction because it's just shift evolution. But that'll introduce some distortion of the base plane. Depending on the experiment, that might not be so important to you. But if you're looking for weak peaks, the quality of the base plane is really critical to your ability to find weak peaks. So any experiment where the range of signal to noise is large and weak peaks are important to you, it's worth going through the trouble of getting as good a clean a base plane as possible. And that means trying to pre-adjust all these delays to get one of the two situations, either a 0 degree first order phase or 180 degree first order phase. 0 order phases aren't important. That just rotates everything. It's the first order phase that can distort the base plane. Mm-hmm.
We have more signal loss in the second part. We put it at T/2 instead of correct to 0.
Well, in this particular case, the marker. In either case, there's some signals relaxing. So in this particular case, where you sample the first point is delta T/2, if we imagine here's T1, and our first point is 1/2 delta T, and the next point will be 3/2 delta T. When we looked at this, right, here's our first point, there'd be a little bit of extrapolation back to 0, right, from that little bit of relaxation loss. But we have the data all sampled here. So in some sense, that's not relevant. We just happen to have delayed sampling. In this case, there's actually going to be a delay of T1 plus this pulse for which there's relaxation. But then we think the initial sampling point is 0. So in that case, our first point appears to us to be at 0, but it's actually a little smaller because of the relaxation during this period. We refocused the chemical shift, but the relaxation happened. But we're only talking typically about a few tens of microseconds. So that relaxation loss is quite small for us in solution. Might be different for you in solids. But there's quite commonly trade-offs between trying to clean up artifacts versus relaxation losses during whatever the scheme is that you're implementing to clean up, clean up the artifacts. So very rarely a free lunch. So we'll come back, we'll see many of these issues, of course, when we start to talk about assignments, the spectra that actually get run when you want to assign spectra. Then maybe, let me reshare the screen. And I'll go back to some of the bits that we skipped over. So when we first introduced the scalar coupling Hamiltonian, I said in solution at high field, we're in the weak coupling limit, that the chemical shift differences between spins are large compared to the scalar coupling. But the strong scalar coupling Hamiltonian has this nice advantage that I mentioned, that the Hamiltonian is isotropic. And that turns out to mean that you can transfer orthogonal magnetization components simultaneously through that sequence. And that experiment then is called TOCSY, or total correlation spectroscopy. And the advantage, as you'll see, is then that whereas something like an inept transfers magnetization from one spin to the next, and that's the end of the story, or cozy, one spin to the next. A TOCSY sequence can transfer magnetization through an entire spin system. Now, there's two problems, of course. One is, how do we generate the strong coupling Hamiltonian? And then the other problem is, how do we analyze what goes on in the strong coupling Hamiltonian? It turns out analytic calculations of the strong coupling Hamiltonian aren't possible for more than 4 spins. And actually doing 3 spins or 4 spins is algebraically extremely complicated. Stefan Glasser did it, but it's more to show that he could do it than anything else. So the next couple of slides show how this works for 2 spins, but that's not at a practical level very interesting, because we really care what happens when you have multiple spins, and then that requires computer calculation. So we could, and of course, since this will transfer any component of the magnetization, I'm not going to do all 3. You'll just have to believe me, or believe the fact that because it's isotropic, it can't matter which one I pick. So here's the transformation of IZ under this strong coupling Hamiltonian. Now, for 2 spins, this is why it's easy for 2 spins, but not for more spins. For 2 spins, IZSZ commutes with IYSY commutes with IXSX. And because they commute, this exponential of the sum can be reduced to a product of the individual exponentials. And that's not, of course, true in general for matrices or operators. And if we had three spins here, that wouldn't work. But then, because that's the case, I can break this up into 3 bits, and obviously the ZZ parts commute with IZ, so I get rid of them. And then I have to work out how IY, SY affects IZ, and then how IX, SX affects IZ. And I don't have diagrams for that, but I can make the diagrams up from our rules. Our rules said if we have a particular commutation relationship, then I can draw one of these pictures. So here then is a picture drawn from this commutation relationship of how IZ evolves under a Hamiltonian that's proportional to 2IY/SY. So I work that out. Zeta is just the product of the scalar coupling times the time. And having done that, I then have to do the same thing for evolution under the IX, SX components. So I work that out. And then if I want to do IZ, I have to exchange the labels on the I and the S spins, just like we did before for the cozy. So here's the result for the first evolution, and then the second evolution. And then I do my usual thing of applying trig functions. So I see then that IZ magnetization evolves into SZ magnetization. And then you also get these various multiple quantum terms. And it's these first two terms that are interesting, because if we start with IZ and we migrate magnetization to SZ, then that SZ magnetization could evolve on to RZ, and from RZ to KZ, et cetera, through the spin system. And while I can't do or don't want to do analytically the calculation for three spins, you can kind of see by analogy how this is going to work. Whereas in the cozy, we evolved to an antiphase operator, and then we were stuck. That couldn't migrate on to the next coupling. And if I go back, I can show that IX will turn into SX, IY will turn into SY. That it's a completely isotropic problem. So now here is what a Toxie sequence looks like. Here, we're just evolving the chemical shift. Of course, the scalar couplings are evolving, but we don't actually care about those. If we went back to, go back to the cozy a second. I should have reproduced. Should have reproduced this slide. So for example, here we have pulse T1 pulse. That's how the Toxie experiment starts. In the case of the cozy, we are interested in this antiphase coherence transfer peak that went from spin 1 to spin 2. Now in the toxi, we're interested in these two peaks, these two coherences. So in what I calculated, when I turn on the toxi sequence, this is going to migrate to spin 2 Z magnetization. And this other one, IY, can migrate to spin 2Y magnetization. Now there's a trick. In the early days, before Mark realized you could keep both of these, you would typically just keep the Z component. If we want to keep both, then it makes a difference how we set up what the toxi block looks like, because we don't want to, if I have X and Z and I apply a Y field, right, then those rotate between Z and X and minus Z. And that will end up being a mixture, then the relaxation will end up being a mixture of T1 and T2 relaxation. The projections into the transverse plane will be T2-like, and the projections onto the Z-axis will be T1-like. And in an ideal case, you end up with the average of R1 and R2. But if I lock the other way, then the component on, in this case, Y, just sees only T2 because it's parallel. It doesn't process back up towards Z. So that decays away much more quickly. So if I'm trying to do this and keep both components, I need to try to keep the relaxation properties of the two components as similar as possible. Otherwise, I lose more magnetization. You might recall then that when we talked about the COSY, this was the signal we were interested in, the antiphase signal. When we did the double quantum filtered COSY, we were interested in this operator. And now for the toxi, we're interested in these operators. So depending on, we have 4 operator terms here, and depending on what experiment we do, we're selecting out one or more of the ones we're interested in, and we want to get rid of the other ones. So then at this point, we turn on something called isotropic mixing. These little delays originally were just to allow shifting of the amplitude and phase of the pulses. And now they can be made very short. The isotropic mixing sequences are, a series of pulses with design phases and amplitudes. Most commonly, the amplitude is constant and just the phases are shifted as a function of time. Although when you get up to 900 megahertz and above, the spectral width, particularly for carbon, gets to be very broad, so then some adiabatic pulses might be used in here. But it's almost all computer calculation now. Every one of these sequences was designed by computer calculation. Originally, people like Malcolm Levitt designed these by having lots of insight into symmetry properties of pulse sequences. So you had things like waltz 4, and then applying a symmetry element, you would get waltz 8, and it would perform better than waltz 4, and then waltz 16. But it's all been taken over by computer calculation now. And what these contour plots show then is the efficiency of transfer between spins at 2 different offsets. So we'd like these to look square. so that we can transfer magnetization from between any pairs of spins in the spectrum that happen to have a J coupling, even if they're very far apart in chemical shift. So you can see the word sequences have the advantage that they can work over a very large bandwidth, but you can see you don't have quite as much of this square shape. Anyhow, there's a huge family of these now that people pick for different applications. But then at the end, we will have transferred magnetization through the spin system. And then to the extent we have magnetization on the z-axis, we have to rotate it down into the transverse plane for detection. Many times, then the next bit here is just a little spin echo that before gradients was pretty common, just again to help clean up the base plane. Nowadays, that may not be there in a sequence you look at. But now you have this network of spins, say going out the side chain of an amino acid, and there's different size J couplings. Magnetization is being transferred simultaneously through all of these J couplings. And you end up then potentially with very complicated coherence transfer pathways. So setting how long the delays should be, how long should we turn on this isotropic mixing, depends on what you think your J couplings are. It's particularly important for protons because the couplings can vary quite substantially. When one's doing a carbon-carbon toxy, say along the backbone, the coupling constants are all about 35 hertz. So there's kind of one optimal value. But the protons, it's more complicated, and there can be some funny behavior. And of course, I've left off the legend here as to which spins we're talking about. So I'll have to add the legend back in because I don't remember. There's one funny case in valines. The magnetization transfers very quickly through the beta hydrogen out to the methyl hydrogens. So you can end up with a spectrum where you have very strong cross peaks, say from the amide hydrogen to the alpha hydrogen, and then out to the methyls, and almost nothing for the betas, just because of this peculiarity in the spin system. Anyhow, here's what you see. So this is a portion for some lysines and just a portion of the spectrum. So here's beta. This is longer and longer mixing times. So at short mixing, relatively short mixing time, you see a cross peak from the amide to the beta. I'm not showing the alpha region, that's somewhere below. And out to the gamma. And when we turn up the mixing time, you start to see some transfer to the deltas. And when the mixing time gets turned up even more, you start to see transfer out to the deltas and the epsilons. But of course, this is all causing relaxation loss. So you can get transfer further out the chain at a cost of reduced signal to noise, so then acquisition time has to come up. Even now in unlabeled proteins, there's a tendency to just use Toxie experiments to assign the side chain. It used to be one did relayed experiments that would be basically back-to-back cozy sequences. So you would go from NH to alpha, then alpha to beta. Or double relay, in which you do 3 steps. And then double or triple quantum experiments, in which you would evolve two couplings at once. The Toxie experiment, in some sense, supplanted all of those because it's one experiment, but also the line shapes are primarily in-phase multiplets. You don't have all these complicated antiphase multiplets that in a crowded spectrum tend to start canceling each other. Negative lobes of one spin cancel the positive lobes of another. The one downside to relying only on Toxies for proton experiments is you can kind of see here, for example, the deltas, gammas are sort of in the same region, and it's possible to have them reversed in order just because of local aromatic groups, etc. So without doing something like a double quantum experiment, you can't be absolutely sure of the assignments in some of the long side chains. If you have labeled proteins, it really doesn't matter because then you're going to be transferring through the carbons, and there the shift differences tend to be much larger and much more diagnostic. Back when we did the first edition of the Cavanagh et al. Book, in fact, Nick found a couple of misassignments in ubiquitin because you could only tell in double quantum spectra exactly what it was you were looking at. And then just to finish today, we'll come back to nosy spectra when we talk about relaxation. The main thing I'll point out is how similar it is to the Toxie. Transfer is just by the Z magnetization here through the nuclear Overhauser effect, but the pulse sequence and the phase cycling is almost identical for a nosy and Toxie experiment. If you look inside a pulse sequence on the spectrometer, you'll see they're basically done exactly the same way. And again, after T1 period here, we have all four operators the same as for the COSY. It's just now we care very much about the Z magnetization being transferred. One of the tricks in nosy experiments is that multiple quantum operator has zero quantum coherence in it. In a small protein, the zero quantum coherence relaxes very slowly and can get converted back into detectable magnetization. So in something like ubiquitin, you can see what are called zero quantum artifacts in the nosy spectrum, very ugly dispersive looking peaks. In a large protein, because they have positive and negative lobes, they tend to cancel. So anything above probably 10, 15 kilodaltons, you just don't see them unless you look really hard for them. But there was also a lot of effort in figuring out how to suppress zero quantum peaks. So if you need to suppress them, James Keeler in particular has very nice combinations of gradients and shape pulses to help suppress zero quantum peaks. One of his clever ideas that really, for obvious reasons, didn't become popular was to have a very inhomogeneous B1 field applied to the zero quantum peaks. I mean, the combination of a swept pulp RF field and a gradient is meant to mimic that, but he had the earlier idea of generating a very inhomogeneous B1 field. So he took one of his probes and crushed the coil to make it very inhomogeneous. And unsurprising work, but unsurprisingly, it didn't take off as a technique other people wanted to adopt in their own labs. They even have a figure for you of the zero quantum peak. And it's sitting on top of real nosy peaks. So they're quite inconvenient when you have them. Right here, you can see this cross peak, the R74. The zero quantum peak is basically completely obliterated the nosy peak. And I don't remember how I suppressed them here. That's probably somewhere in the book. All right, so maybe the nosy, stopping here with just seeing a nosy sequence leads to the question of what's the nuclear Overhauser effect? And that leads to relaxation. And as I said in the beginning, tomorrow will be our first relaxation lecture. Any questions online? If not, Elsie. So since I just posted the problem set 3, presumably no one has had a chance to look at it. So maybe we'll talk about it some tomorrow as well, if you get a chance to take a quick look at it tonight. The goal is to gradually build up HNCO sequence. So an HNCO sequence transfers magnetization from the amide hydrogen to the nitrogen to the carbonyl and then back again. So you'll be putting together a series of either INEPs or HFQCs or HMQCs, basically pasted together to move the magnetization one step at a time. 2 steps out and then 2 steps back. So it's a fairly long problem because it's designed by Stefan Zizek. So you start doing something relatively simple and then start to add more and more bells and whistles. So for this first go around, we won't do all the bells and whistles because when we start to talk assignments and 3D experiments, it'll be easier to then go back and finish. So I'll take a look and send out an email about how far you should get. Actually, I can probably just tell you right now. Let's do that. Because I don't know if Whitney is around to send out his email. Right, so in the beginning, oh, I should share the screen again. Yes, hold on. So here are the transfers. You want to go start with amide nitrogen magnetization, go to transverse amide hydrogen Y minus Y magnetization. And hopefully now you know that that's an X pulse, does that. And then we want to evolve into this antiphase operator using something that looks like an inept, and then switch the coherences from antiphase on X to antiphase on nitrogen, evolve the nitrogen carbonyl coherence. So now we have antiphase nitrogen with respect to the carbonyl, and the hydrogen just comes along for the ride. You might have to worry about not accidentally refocusing that coupling. And then we can turn antiphase on nitrogen into antiphase on the carbonyl, and then come all the way back. So that's what you want to do. And here, the carbon, the hydrogen to nitrogen coupling, I said, is about 90 or 93 hertz. The nitrogen to carbonyl coupling is about 15 hertz. So how long the delays are will depend on the coupling. It's fairly common to make the delays a little shorter just for relaxation losses. So the ideal delay in B would be 1/2J, but Stefan suggests maybe you would only use 80% of that in order to make things a little shorter because of relaxation. And probably if you thought about A, B, and C, that would be more than enough. And then the rest of this about constant time, etc., we can worry about as we get to assignments and more of the bells and whistles. So if you have time to take a look at it, then we can talk a little bit more about it tomorrow. If there are residual questions about problem set 2, of course, I'm happy to answer them. The key is posted. Is that a yes?
Yes, there is
Okay.
a,
Uh-huh.
I could work out the, what happens to the spin echo with an exhaust cycle, phase cycle, with just chemical shift offset.
Yes.
How do I do it with J coupling?
It's pretty complicated
Yeah. Is there-
because it generates a lot of terms,
Yes.
and you know every year or two I waste time thinking I must have a way of simplifying it, and I never find a way of simplifying.
Okay.
So yeah, I don't have a good answer to that.
Okay. I also have some questions regarding the coding. So if you could look at the slides.
Mhm. Okay, let me share the screen again. Go back up to the cozy.
Particularly when we're talking about frequency discrimination,
Mhm.
cozy line shapes. Yeah, this is this slide. So here, I'm struggling to understand which. So one of those, the I1 minus peak is the diagonal peak, right?
So I1 minus cosine omega 1 is the same frequency in
Right.
both dimensions. So that's going to be a diagonal peak.
And I2 minus, that is the transfer term, which is the cross peak, right?
So here, cosine omega 1 T1, I2 minus is the cross peak
Right.
that started on I1 and was transferred to I2.
Now, I guess the diagonal peak is dispersive because it carries that I in front of that one.
So the I is a 90-degree phase shift
Right.
relative to the other peak. And of course, it's up to us whether we want to phase it to be dispersive or absorptive. So I could apply a 90-degree phase shift, make the diagonal absorptive, but then the cross peak becomes dispersive.
Right. Now, my question is, so that cos pi j t1 can be expanded as e to the I pi j t1 plus e to the minus I pi j t1. I can combine that with the chemical shift term.
Right?
That becomes omega 1 plus pi j and then omega 1 minus pi.
And it's in phase.
Yes.
So the cosine will be in phase.
And then the sine 1 is e to the I pi j t1 minus e to the I minus I pi j t1 over 2I. And I turn that 1 over I into a minus I on top, then I get the I hanging to both terms.
So of course it's going to be an antiphase multiplet.
Yes.
Because of the sign. And then the the I in the, so it looks like, right, that that I should mean this has the same phase as that.
Yeah,
And it doesn't if you actually do the Fourier transform. So you have to actually do the Fourier transform to see that the I on the 1/2I kind of comes out in the wash. And right this moment, I explain why that happens. Right this moment, I can't tell you exactly why it happens. I know it happens if you sit down and do the Fourier transform. So you just have to think of the sign as giving an antiphase multiplet
yes,
without thinking too much about that extra I.
yeah, that makes sense. It gives an antiphase doublet and the cost term gives an in-phase doublet. But the fact that one is dispersive and the other is absorptive is a big driver to develop a quantum field that goes here.
That's right.
Right.
Because the dispersive tails, usually we would
Yeah.
phase the diagonal to be dispersive so that the cross peaks are nicely resolved, but then the cross peak near the diagonal gets obliterated by the tails.
Yeah, just that when I look at the Cartesian terms, it makes sense because it's I1x one case and I2y in the other. So
Right.
there it makes sense that one's absorbed to the other is dispersive, but when we go down to these lowering operators, it doesn't show up. Thank you.
Yeah, I'll think overnight if I would
Right.
an answer that doesn't involve actually grinding through the Fourier transform.
Right.
Okay, see everybody tomorrow.